All right, let's dive right into this. Welcome to today's explainer, where we're going to demystify the hidden, almost totally invisible physics behind how the screens on our smartphones, smartwatches, and TVs actually work. If you've ever looked at a stunningly bright, perfectly black OLED display and wondered exactly how that light makes the journey from a microscopic molecule directly into your eye, well, you're in exactly the right place. We're going to break down the complex mechanics of something called OLED outcoupling, and I promise you, by the end of this, you'll be looking at your phone screen in a completely different way. I want to start off by posing a central paradox to you. Picture this. You've got a team of the absolute best chemists in the world. They grind away in a lab for years and finally engineer the perfect light-emitting molecule for an OLED. I mean, it's flawless. It converts 100% of its electrical energy into light. But when you actually build a display out of it, the screen is still incredibly dim. Why? Because as it turns out, creating the light is really only half the battle. If the light you just made gets permanently trapped inside the device, your screen just stays dark. So here's our roadmap for today. We'll start with the OLED light trap, look at the 5 paths a photon can take, and then jump into the horizontal emitter solution. After that, we'll navigate the optical microcavity, discuss why displays specifically need internal fixes, and wrap up by totally rethinking OLED efficiency. All right, Section 1, the OLED light trap. Think of this as the engine versus the choke point. To really wrap our heads around the massive difference between internal chemistry and external brightness, we need to define the absolute most critical term for today, light outcoupling. Light outcoupling is simply the fraction of internally generated photons that actually manage to escape an OLED into the air, rather than just getting stuck bouncing around inside the device. I really want to stress this. A brilliant, vibrant display isn't just about making photons. It's all about freeing them. And this brilliantly illustrates what we call the engine versus the choke point. So think of the internal quantum efficiency, or IQE, as your engine. Modern OLEDs are literal chemical marvels. They essentially solve the spin statistics problem, meaning their IQE sits at a beautifully perfect 100%. Every single electron injected makes a photon. But because of poor outcoupling, all those newly generated photons get dumped into this brutal survival funnel. For a lot of conventional flat OLEDs, the outcoupling limit chokes the light output all the way down to around 20%. So you've got a chemically perfect device with 100% internal efficiency, but it drops to a dismal 20% external quantum efficiency. That is a massive, massive loss of optical power. Moving on to Section 2, the 5 paths of a photon, or, where does all that light actually go? If we're losing roughly 80% of our generated light, we really have to ask where exactly it's disappearing to. When a photon is born inside the emissive layer of an OLED, it's almost like it's dropped into a microscopic pinball machine. It essentially has 5 potential paths, or optical channels, it could get. The first is the air mode. This is the light that actually escapes into the air and hits your eyes. This is the only useful channel. The second is the substrate mode, where light hits the glass but bounces right back due to total internal reflection. Third is the organic waveguide mode, where light just propagates entirely sideways inside the organic layers, totally trapped. Fourth is the highly lossy surface plasmon polarifon, or SPP mode, where the photon's energy couples to the metal electrode and is completely wasted as heat. And finally, absorption, where the light is simply absorbed by the materials themselves. An OLED is essentially a stack of microscopic thin layers. And the core issue here is that the organic layers and the glass have way higher refractive indices than the air outside. It basically acts like a tiny optical hall of mirrors. Because of these refractive index mismatches, the internal optical power is permanently trapped by total internal reflection and plasmonic coupling. The light just bounces sideways or gets absorbed as heat. It is an incredibly hostile environment for a photon just trying to make an escape. Okay, Section 3, the horizontal emitter solution. This is all about steering light right at the source. To find a brilliant way out of this light trap, we have to look down at the molecules themselves to steer the light right from the moment it's created. Emitter molecules radiate light kind of like tiny oscillating electric antennas, which we call transition dipoles. Now, these dipoles have a specific orientation. A vertical emitter has its dipole moment pointing straight up and down, perpendicular to the substrate. A horizontal emitter, on the other hand, has its dipole moment lying flat, completely parallel to the substrate. Before we can try and engineer a solution, we have to understand our baseline here. If you just mix these emitting molecules randomly into a thin film, what kind of orientation do you actually get? You might intuitively assume it's a clean 50-50 split, but it's not. In three-dimensional space, we have 3 axes, right? X, Y, and Z. The X and Y axes are horizontal, parallel to your screen. Only the Z axis is vertical. So because 2 out of the 3 spatial dimensions are horizontal, random molecular orientation is inherently 2/3, or roughly 67% horizontal, and only 1/3 vertical. That's the physical baseline we're working with. Now, what's really interesting about this is the core physics rule governing these tiny antennas. A dipole radiates light most strongly perpendicular to its axis. That means a vertical dipole, one standing straight up, radiates its energy sideways, right along the plane of the device. This is fatal for efficiency. It efficiently couples its energy directly into those lossy surface plasmon polariton modes along the metal electrode, and it's instantly lost as heat. But a horizontal dipole, one lying flat, radiates its energy upwards and downwards. This beautifully avoids that sideways trap and couples favorably into the radiative escape modes that actually let light leave the screen. Section 4. Navigating the optical microcavity. Let's actually prove the math of outcoupling. It's time to run the numbers and explore how we calculate the tangible impact of this orientation. I want you to consider this. Mathematically, how much does orientation actually matter? Are we talking about a tiny, marginal gain here? Or does forcing these molecules to lie flat instead of orienting randomly make a truly transformative difference to the tech? Let's walk through the multiplier effect. Say, under condition A, with random orientation, we have that flawless 100% internal chemistry, but our outcoupling factor is a miserable 0.20. Our total efficiency is just 20%. Now let's look at condition B. We don't change the chemistry at all. We literally don't create a single extra photon. All we do is highly orient those emitters horizontally and tune the optical stack, bumping our outcoupling factor up to 0.35. Boom, our total efficiency jumps to 35%. That is a massive 75% relative increase in efficiency. We get all that extra brightness just by acting like a traffic cop, redirecting the light that was already sitting right there. Actually, scratch that, it's not quite that simple. We have to be precise. An OLED isn't just free-floating in space. It is a highly tuned optical microcavity. Outcoupling doesn't just rely on making the emitters lie flat. You have to optimize that horizontal orientation alongside the exact physical position of the emitter, the wavelength of the light, the layer thicknesses down to the nanometer, and the refractive indices of every single material in the stack. It really is a complex, beautifully balanced optical equation. All right, Section 5, why displays need internal fixes, and how this applies in the real world. Up to now, we've been super deep in the physics. Let's pull back and apply this directly to the actual gadgets we hold in our hands every single day. Why do we go through all this trouble at the molecular level? Why not just slap a big magnifying lens on top of the screen to pull the trapped light out? Well, for OLED lighting panels, like overhead bulbs, you actually can do that. You can use rough, scattering structures or lenses to yank that light out. But displays, they demand razor-sharp pixels, perfectly smooth surfaces, and strictly controlled viewing angles. If you put a scattering lens on your smartphone, your text would become an unreadable, blurry mess. This is exactly why planar displays absolutely demand horizontal emitters. They provide an invisible internal fix, boosting efficiency right at the source without adding unacceptable bulk or blur to your screen. The way chemical engineers actually pull this off is, frankly, mind-blowing. By designing the molecules to have specific planar shapes or elongated structures, they can literally force the molecules to lie flat during manufacturing. They use these host-guest interactions, it's almost like interlocking puzzle pieces, to lock the emitting molecules into a horizontal position as the thin film is deposited in a vacuum. Thanks to this crazy modern chemical and steric design, the latest systems can successfully engineer over 90% horizontal alignment. We are quite literally manipulating physical geometry at the atomic scale to control light. And finally, Section 6, Rethinking Total OLED Efficiency. Time to dismantle some common myths. So the crucial point is really captured by busting these 3 myths that even tech enthusiasts sometimes get wrong. First, the myth that perfect internal efficiency equals a perfect device. As we've seen, IQE completely ignores light trapping. Perfect chemistry times a 25% outcoupling still leaves you with only 25% external efficiency. Second, the myth that a random mixture of molecules gives you a clean 50-50 split. Because we live in a 3D world with 2 horizontal axes and 1 vertical, random is inherently 2/3 horizontal. And third, the myth that better orientation creates more light. It doesn't. Orientation doesn't change the quantum yield or create new excitons. It just acts as a physical steering wheel, redirecting where the emitted optical power actually goes. Outcoupling is truly the ultimate barrier to theoretical maximum efficiency. To pull this whole shebang together, the overarching takeaway from our explainer today is that horizontal emitters revolutionize OLED efficiency by acting like a highly efficient transmission system. They don't build a bigger engine, and they certainly don't create more excitons. Instead, they guide the photons that those excitons already produce far away from the lossy, heat-generating metal traps and channel them directly into the optical paths that can actually escape the glass and reach your eyes. And that leaves us with a pretty fascinating thought. The future of the displays in our pockets and in our living rooms isn't just about making better light. It's entirely about setting that light free. As engineering pushes the boundaries from 90% toward a theoretically perfect 100% horizontal alignment, we have to ask what insane new levels of battery life, sheer brightness, and entirely new device form factors will become possible when we finally completely escape the light trap. Just something to ponder the next time you wake up your phone screen. Thanks so much for joining me on this explainer, and keep questioning how the tech around you actually works.